Okay, so good afternoon. Thank you for being here. I am Matteo Picozzi, professor and director of the Seismological Research Center of OGS, the National Institute of Oceanography and Applied Geophysics. I'm really glad to be here this afternoon with my esteemed colleagues from Japan and Italy to discuss about the seismic risk. And we defined this title just to give an overview of what we do in emergency situation and what we plan to do as a research to mitigate the seismic risk. So I also honored and glad that the Ambassador Vattani is here, and I invite him here on the stage to say a few words. Thank you.
Grazie, thank you very much. Just a few words to welcome you to this event. I have just returned, in fact, for a few days I managed to escape Expo, which is not easy because normally we spend all our days and nights here at the pavilion. But I was there because of a very important event, which is by the Italy-Japan Business Group. And it is, in fact, a forum which puts together the top industries in Italy and Japan. So it's all about the future. It's all about innovation. It's all about technology. It's all about industry. And this is very important to us because to have a pavilion as the one that we have now here in Osaka for 6 months. 6 months sounds sometimes like a long time, but in fact it's quite a short time if we consider that this is a platform, a precious platform that we have here in Japan to present Italy's culture, of course, to present Italy's territories, to present Italy's high-quality products, and the made in Italy that all of us enjoy. But at the same time, it is an opportunity to come together and to put together some fruitful cooperations in fields that are important to Italy and to Japan. Why did I start by talking about the business group? Because all the Japanese representatives of very important industries all stressed the opportunity of Expo, all knew about our pavilion, and they all count on this platform to really accelerate and mobilize Italy's and Japan's innovation, the world of innovation, about what we most care about. And how can we identify what we most care about? You can see some of it in this pavilion, because this pavilion is not only about Italy, it's about Italy and Japan. You can see it when you start the visitor experience. The first person that you meet, the first person that greets you is Ito Mancho, who is a young Japanese ambassador, I would say, whose portrait was painted by, nonetheless, than Tintoretto. So this is what we talk about in this pavilion. It's about not only what has happened between Italy and Japan, but what can happen between Italy and Japan. And so when I was telling you how do we identify the new sectors, the most important sectors that we have to concentrate on, well, we have an action plan. We have a real action plan which was built because of the strategic partnership that started between Italy and Japan last January 2023, when our Prime Minister, Giorgia Meloni, and the then Prime Minister of Japan, Mr. Kishida, decided to raise the level of our collaboration, of the collaboration between our two countries. And what is this collaboration about? Many sectors that are close to our interests. One of them is something that we share. Because when we talk of seismic risk, and just as if you see us talking about multi-year planning, for example, this is something that is very close to Italy and to Japan. So it is natural that there is a dialogue about this kind of, in this kind of sector, which we will, today we are talking about this issue, but this issue will be with us in the next months. Consider that the Minister for Civil Protection, Minister Musumeci, will be visiting our pavilion and will organize a series of events here in July this year. And again, we will be talking about these subjects. So it's important that we consider whatever we do here has to be connected, has to have a kind of time frame that must connect us to the next time we will address issues like the one we are addressing today. So thank you very much. I'm very grateful to the Italian National Institute of Oceanography and Experimental Geophysics. We're very happy that you chose the Italian Pavilion to hold this, this meeting. And so I wish you the best for this meeting, and thank you very much for being here.
Thank you, Ambassador. So I will say that we can take here on the stage, so I invite Professor Enescu, Professor Nanjo, Professor Kato, Professor Zhuang, and Dr. Oshiba and Dr. Gentili to join us here on the stage. And we are going to give a few presentations of different topics from the Japanese point of view and the Italian point of view on this issue of seismic risk. I will be the first. Can you hear me? Yes, okay. So, yes, I'm going to just give an overview of what is the situation in Italy concerning the monitoring of seismicity. And before to start with the Italian case, let me clarify which is the problem that we have. Here in the map, you see the hazard at the global scale. So red and dark red areas are those with a higher hazard. And here you see in the 50s the distribution of megacities that were few and quite far from a place where the hazard is high. But then, if we look at what is the situation just a few years ago, you see that there has been an incredible increase of the number of megacities, so a high concentration of urban people in area at high hazard, which led to have a dramatic increase of seismic risk. And this is true at all the scales. This is true also for Italy. You see on the left the distribution of microseismic intensity, so the level of damage in the last 1,000 years in Italy. And you see that dark red, purple, and black points are municipalities that were destroyed by earthquakes. And here on the center, you see the distribution of strong earthquakes. So you can imagine that the combination of this kind of information led Italy to have a high level of hazard. And so since the cultural heritage and the population is exposed to this risk, the risk is really high. Let me spend also a few words about my institution. So we are one of the 14 national public research institutes under the control of the Ministry of University and Research. Most of them in black are placed in Rome, while we are in blue and we are placed in Trieste, so in the northeastern side of Italy. And OGS has as a field of activity, of expertise, the oceanography, the geophysics, and also the seismology. So we are organized in 4 main sections. We have the section of oceanography, which deals with the investigation of the physical, chemical, and biological condition of oceans and seas. We have the section of geophysics that aim to understand how the Earth is made. Then we have a center for the management of infrastructure, and especially the Laura Bassi, which is a icebreaker ship which reached the farthest place in Antarctica and is used by the Italian community to reach Antarctica every year and to do research in that area. And then the Center of Seismological Research, which I direct, which is dedicated to the topic of our talk. So the distribution of our institute is a little bit spread in Italy, even if it is concentrated in the northern eastern part, but we have also special offices and observatories in different parts of Italy. And we have different missions, of course, according to the different section. We aim to understand the sea and the ocean, understand the earth, the polar areas. Of course, we are really engaged with the open sciences. And this is strongly related to the topic of today. So in the mission of disaster risk, we aim really to understand how to manage the disaster risk and build a prepared and a resilient society. And so here I just took a picture from what happened in Italy in 1976, so almost 50 years ago. There was the Friuli earthquake with severe damage, many people that were killed. And you can see on the right in the image that each dot is a municipality which felt or was damaged by the earthquake. And this is also important to show that one earthquake was able to affect a very broad area. So earthquakes does not care about the national border. And it is really important also to cooperate among countries to improve our level of knowledge. And this is how and why in 1977 was created my institute, my center. And as you can see on the right, we have a high number of seismic stations that today are monitoring the area, the southern margin of the Alps, where strong earthquakes occur. But in the picture, you see also the stations from other countries, the neighbor countries, which since many decades are exchanging with us the data. So I think this was one of the first examples where the cooperation among countries exchanging data and tools was put in operation to improve our capability to mitigate the seismic risk. And after that, since a few years, starting from the 2010, we have this European initiative, EPOS, ERIC, which includes 18 European countries defining the tools and the strategies to share the data and also to share the product almost in real time. You see on the right, this is nowadays the distribution of seismic stations in Italy. We have almost 2,500 seismic stations, so a density of stations that is comparable with the Japan networks. We look at Japan always as an example to follow. No? You are our beacon for the research on this topic. And I think that now the amount of seismic station is comparable. And we have also characterized the site amplification of all these stations that can be found, this kind of information can be found at that site. So now that we have all this data and we record a lot of microseismicity, and this is something that occurs also in other countries around the world, we are able and we start to learn something more about the preparation process of large earthquakes. And there are a number of studies, I just selected a few of them, that are showing us that when we study the characteristics and the spatio-temporal evolution of small earthquakes, we can catch maybe some precursory pattern before large earthquakes. You see here on the top the L'Aquila case in 2009 in Italy. You see here from Professor Kato the case of Kumamoto in Japan, but also the Kahramanmaraş earthquake in Turkey 2 years ago, the Chile megatrust earthquake, and the 2011 Tohoku-Oki earthquake. In almost in all these cases, we observed in a retrospective way that the small earthquakes are somehow clustering and then defining an area where the future strong earthquakes nucleate. So studying small earthquakes is something that can teach us how large earthquakes are generated. And we also developed a system, a service, which characterize not only the spatio-temporal evolution of small earthquakes, but also their characteristics. And especially we developed a strategy to, which is called the Ramones, the Ramones service, where we characterize the earthquakes in terms of seismic moment and radiated energy. And once that we calibrate a model, a scaling model between these two source parameters, we can look when new earthquakes happen, if the radiated energy is compliant with the model, or there is a deficit in energy or an excess in radiated energy. So this is a kind of proxy for the stress and for the crustal stress. And so we can see that not only the spatial and temporal evolution of seismicity for L'Aquila and between L'Aquila and Amatrice earthquake change. So here we observe that there was a migration of seismicity towards north, which is also shown here on this plot, from L'Aquila to Amatrice. But there was also a significant change in the stress, and the small earthquakes are able to provide this kind of information. So somehow studying small earthquakes can learn us something about the state of the faults before that they break. And another example is studying the ground motion anomalies. So when we characterize the evolution of the ground motion with respect to the scaling, so the distance and the magnitude, we obtain a medium model that describe this kind of a trend. But then we can have earthquakes that are able to generate some extra ground motion or some deficit of ground motion that we are able to measure. And when we follow the temporal evolution of this parameter that we call ground motion anomalies, indicated by this delta BA, and we analyze for still, again, for the L'Aquila earthquake, its evolution in time, we see the same kind of drop just in the activation phase before the large earthquake. So both from source parameters, what we have seen before, the energy index, and the ground motion, which does not depend by source parameters, we obtain information that maybe in future could help us to set up some early warning system. This is the reason why we are studying small earthquakes, and to do this we develop networks with seismometers, accelerometers, also important the geodetic network to measure the long and small deformation of the crust. And we monitor this sector of Italy in the northeastern side. And you see on the top left that there were a lot of strong historical earthquakes in this region. So our activities are directed to understand the generation process of the large earthquakes, but at the same time we are also active with respect to the civil protection, because we provide to them the official information to help the management of the risk soon after a large earthquake. So we are engaged to localize and characterize an earthquake in real time, to locate it, to estimate the magnitude, and then to estimate the ground motion that you see on the right. So the shake map provides us an image on the ground shaking, and with the color from white to red, we define the areas where the ground motion was most severe. But we don't stop here, because since in the last years we have characterized for the whole region the spatial distribution of the exposure, so we characterize the buildings in each municipality in terms of floor, number of floors, age, and typology of construction. We can use this piece of information spread in the whole area to create a workflow that goes from the left, so we characterize in real time the ground motion after an earthquake. Then we combine this information with exposure and with the fragility function, which provide us the information about the potential damage of a structure given a level of ground motion. And we combine these three pieces of information in a map which provides the expected damage. And this is something that can be used by the local civil protection to improve their rescue activities, and also some estimate of the losses. And we developed a tool that is running in the civil protection control room in Friuli Venezia Giulia and in Veneto. And so after an earthquake, all the workflow that you have seen provides to the rescue teams this kind of map with the indication of which municipalities have suffered the damages, and we estimate also the level of loss. So as you have seen, we have activities that goes from the understanding the physics of the earthquakes to something that is really practical and is helpful, I hope, for the people. Besides that, we are installing cost-effective strong motion in each municipality to improve our estimation of the ground motion. So now we reached a number of 430. Then, as a future development, we just bought a few months ago 5 DAS, so the distributed acoustic sensing, which is a new technology that exploits optical fiber, and through impulse, laser impulse, is able to provide information about the strain rate. And this kind of technology can be used, is totally new, since a few years is under investigation, can be used to monitor with a really, like to have a high dense network along a specific line. And together with the region Friuli Venezia Giulia, we decided to install this DAS to monitor the fault area where the strong earthquakes are generated, and also the basin where we want to study the site effects. Finally, and I'm going to close my presentation, we are active also with the fault-based seismic hazard. So whenever we know the mechanic of a fault, because we are better characterizing it, we want to use this information to improve our hazard estimation. And finally, we are also engaged with the use of information from the citizen. So in the right, you see the distribution of reports collected after an earthquake in Croatia. And this is the information provided by the citizen in Trieste. So this is also important, because the people is, from one point of view, is the weak part of the workflow chain. But at the same time, they can become also active, providing feedback and behaving in a correct way if they know about seismic risk. And the last point is that we are also active with the trained volunteers. So people working for the civil protection that after an earthquake provide immediately us with an information about what they felt in different municipalities. So I thank you for your attention, and this was just an overview of what we do at the OGS. And now, according to our program, I think after me there is the presentation of Dr. Oshiba about the activities of JMA.
Okay, thank you for introducing me, and so thank you very much for inviting this important meeting. So today I'd like to explain timely information just before and after strong shaking, that is ASCII early warning and rapid report of seismic intensity. At first, please note in advance that the alert sound is made in this presentation for explanation of ASCII early warning. Okay? So what is ASCII early warning? Okay, ASCII card and P wave, S wave radiated from the source, and seismometer nearby detect them, and rapid transmission, quick analysis. It is possible to inform people before strong shaking. Okay, so this ASCII early warning is different from so-called earthquake prediction. We are aim at timing after ASCII occurrence, but before strong shaking. I will show an example using this video. This is from first event of the 2016 Kumamoto earthquake. Okay, I will show this is a video from NHK. NHK is a public broadcasting TV channel in Japan. And I will show here the real-time shake map using data assimilation technique. Okay, so this is the event of April 14, 2016 to 9:26 p.m. Magnitude 6.2 event. So because of that 9 p.m., NHK broadcast a news program. Okay, shall we go?
やはりなかなか自分なりの方法を見つけられなくて焦りとか不安を募らせる学生がいたというのも
緊急地震速報です。強い揺れに警戒してください。
So ASCII early warning issued from JMA. And strong ground shaking is predicted, and Kumamoto, Fukuoka, Nagasaki, Miyazaki prefectures.
熊本県、福岡県、長崎県、宮崎県、山口県、愛媛県、佐賀県、大分県、鹿児島県では強い揺れに警戒してください。怪我をしないように身を守ってください。倒れやすい家具などからは離れてください。
So secure your safety and away from heavy
熊
furniture.
本県、福岡県、長崎県、宮崎県、山口県、愛媛県、佐賀
This is
県、
the scene
大
of the
分県、
Kumamoto
鹿児
city.
島県に出ています。強い揺れに警戒してください。怪我をしないように身を守ってください。倒れやすい家具などからは離れてください。
Okay, so after shock occurred
テーブル
like
や
this.
机の下に隠れてください。熊本の現在の様子です。カメラが大きく揺れているのがわかります。揺れが強い地域の皆さん、落ち着いて行動してください。熊本の現在の様子、
Earthquake was
カ
observed
メラが
at Kyushu
横に
region
大きく揺れているのがわかります。
9:26 p.m.
NHK の各放送局からの情報によりますと、9時26分頃、九州地方で揺れを感じました。震源が海底ですと津波の恐れがあります。海岸や川の近くからは離れてください。現在の熊本市の様子です。今、震度7を観測した地域があります。熊本県熊本地方で震度7を観測しました。揺れが強かった地域の皆さん、
So pay
落ち着い
attention
て
to
行動してくだ
tsunami.
さい。
Okay, pay attention to tsunami at coastal area and seismic intensity 7 Kumamoto region and seismic intensity 5 low also Amakusa regions. Okay, something like that. This is a typical sequence of the earthquake early warning and rapid report of seismic intensity. Okay, so I will explain the timing of warning and information from JMA. So about several seconds after an earthquake early warning, and 1 or 2 minutes after an earthquake, seismic intensity information, and 3 minutes first tsunami warning advisory, and 5 minutes earthquake and intensity information, and 10 minutes something tsunami information, and 15 minutes estimated seismic intensity distribution map. That is similar with the shake map. Okay, today I like to talk about earthquake early warning and seismic intensity. So I will explain the seismic intensity and earthquake early warning. Okay, seismic intensity. Okay, JMA seismic intensity ranging from 0 to 7, and important is seismic intensity 5, and seismic intensity 6 are divided by 2. That is 5 lower, 5 upper, 6 lower, and 6 upper. So totally 10 degrees are used for representing the strength of strong shaking. So this is the approximate relation of the JMA scale and modified medical scale, MSK scale. Okay, so this seismic intensity, JMA seismic intensity is measured instrumentally at present. So instrumental observation started in 1996, so just after the Kobe earthquake. So before 1996, seismic intensity is measured human sensation. But in 1996, we introduced instrumental observation. Because of the instrumental observation, it becomes objective observation, and dense network automatic transmission can enabled. And seismic intensity is measured not only amplitude, but also duration and frequency of the seismic waveform. And seismic intensity is one of the representation of strength of ground motion. Okay, so the seismic intensity measured conducted at the present 4,400 stations nationwide by not only JMA, but also municipalities and NID, that is KNET. So this is around here, the Osaka region. Okay, Osaka regions, because of the Osaka is a very populated city, so the interval of the seismic intensity meter is less than 5 kilometers, so quite dense observation network. And in 1995, which means before instrumentations, about 150 stations. At the present, 4,400 stations, about 30 times. Okay. So why seismic intensity in addition to hypocentric and magnitude? Okay, so there are the two events. Okay, almost same location, same magnitude, almost same focal depth, and almost the same focal mechanism. But focusing around here, okay, around here, this event is stronger, and focusing around here, okay, this event is stronger. So this means that distribution of seismic intensity is not always the same, even when the same hypocenter, same magnitude, and the same focal mechanism. But distribution of seismic intensity is sometimes different, which means information of hypocenter and magnitude is not enough for imaging a distribution of ground motion. Actual observation of ground motion is important for estimation of potential damage area. So, seismic intensity observation. Okay, so there are three kinds of expression for seismic intensity depending on elapsed time. For example, about 1 or 2 minutes after an earthquake, so sub-prefecture image like this. And about 5 minutes, so at each site. And about 15 minutes map image, that is similar with a shake map, is issued from JMA. Okay, so this seismic intensity is used for a trigger of emergency action of the government, national government, local government. Especially when, for example, it's Prime Minister official residence, they started emergency assembly team conference when seismic intensity 6 lower or 5 upper for Tokyo metro area is actually observed. And cabinet office, they started the estimation of damage in case seismic intensity 4 or larger is actually monitored. And the defense agency and Japan Coast Guard, they started their investigation using their aircraft in case seismicity 5 lower or larger is observed. And Metropolitan Police Department and Fire and Disaster Management Agency, they started their investigation using a police car and firefighter car. And NHK and other TV channel broadcast seismic intensity information. Okay, so next is I will explain earthquake early warning. Okay, earthquake early warning is operated, tested in many countries and Japan, and Taiwan, and Mexico, United States, and a European country, including Italy. Professor Picotti is also an expert of earthquake early warning research. Okay, so in Japan, in this country, nationwide earthquake early warning has been operated by JMA since October 2007. 18 years ago. So GMA-EW is a nationwide service and issued to general public using TV, radio, smartphone broadcasting mail. So there is a two categories for GMA-EW. One is called forecast and the other is called warning. Forecast is for advanced users. Advanced users means, for example, railway company or elevator company, so some expert. So this forecast is issued in case seismic intensity 3 or larger is predicted. And the range of seismic intensity 4 are especially specified in the forecast message. And warning. Warning is a service for general public. So warning is issued, seismic intensity 5 low or upper is predicted. And this warning message is broadcast by TV, radio, and smartphone mails. Okay, so the sound. No? Oh, no sound. Okay, so I will skip the sound. So next slide, I will explain the performance of GMA-EW during the 2011 Tokyo earthquake magnitude 9 event. Okay, so here, yellow region means forecast region, which means seismic intensity 4 predicted, and pink region means warning region, which means seismic intensity 5 low is predicted. So I will show the observed waveform, observed these four stations, and here is the okay. So here is the lapse time from the origin time, first forecast and first warning, and here is for this earthquake, totally 15 messages issued, and this means the estimated magnitude at that time. Okay, I will show it. Earthquake occurred. And P wave, S wave, radiated from the source. And the first station all detect P wave and quick analysis and the first forecast and the warning issued. At that time, cellular phone and TV broadcast a warning message. Okay, so here, around here, still weak shaking. First strong shaking, first red point appeared from now on. Which means GMA-EW worked well, and EW message about 50 seconds before strong shaking. Okay, this is 11th issurance, 12th issurance, magnitude estimation 7.9. Magnitude was estimated 8.0. 14, magnitude was estimated 8.1, and 15, this is the last message. So far, so good. But the problem occurred from now on. So focusing around here, contour regions, background yellow, which means seismic intensity 4 was predicted. But actually, red point appeared like this. Actually, seismic intensity 6, upper 6, lower, actually observed. So around here, under predictions. So this is due to the large extent of the fault rupture of the magnitude 9 event. So this is the first problem. The second problem occurred during the aftershock. So this animation shows the aftershock activities, March 3rd, March 4th, March 5th. So this is a normal situation. And March 9, foreshock, and March 11, main shock. After that, something like that. So seismic activity, aftershock activity, quite active. So sometimes multiple aftershock, 2 events or 3 events occurred simultaneously. In this case, system confused. System misinterprets the multiple small event to be a large single event, which leads to overestimation, magnitude, and then false alarm. So addressing this problem, huge extent of fault rupture and multiple simultaneous event has been an important project after the Tokyo earthquake. So addressing the problem of multiple simultaneous earthquake, IPF method was incorporated into GMA-EW in 2016. Okay, before IPF method, so using arrival time, hypercenter, that is latitude, longitude, depth, focal depth, origin time are estimated. And using the hypercenter data and amplitude, magnitude is estimated, 2-step approach. But in IPF method, amplitude data is used. Amplitude data is used for hypercenter determination. So hypercenter magnitude estimated simultaneously. By doing so, we can avoid mislocation of hypercenter where amplitude is very small. Okay. So addressing the problem under projection shaking, problem method was incorporated into GMAEW 2018. Problem method algorithm is very simple. Monitoring surrounding station, 30 kilometers or something. Actually, strong ground motion monitored. In this case, a warning is issued. So no missed alarm, and we don't need to wait 3 seconds for magnitude estimation. So this problem method worked well during the Hokkaido Eastern Iburi earthquake. Focal depth 37 kilometers, magnitude 6.6 events. So this is a distance and observed PGA. And this is a prediction using a GMP, ground motion prediction equation, using hypercenter magnitude. So focusing around here, so we can see systematic deviation from GMP, ground motion prediction equation. This means, so even when hypercenter, the magnitude are estimated precisely, ground shaking is under-predicted. But the problem worked well. So problem worked well, and the problem avoids under-prediction. And problem method, okay. And problem was earlier than source-based method by 3.1 seconds. Okay, so from viewpoint observation, OBS is incorporated in GMAEW in 2019. SNet data, SNet is the ocean bottom seismometer network, 150 ocean bottom seismic network deployed by NYED. So this ocean bottom seismic network data is also used for the GMAEW operation. And long period ground motion, prediction of long period ground motion is also incorporated in GMAEW. So this is an example during the Tohoku earthquake, the tall building. So this building is at Osaka, next island of Osaka city. Okay. So at that time, long period ground motion continue long duration, 10 minutes or something. So because of the experience, GMA decided to prediction of long period ground motion into GMAEW operation. So that is started from February 2023. Okay, so EW is a tool for securing safety just before strong shaking, and seismic intensity is an index of strong shaking. Okay, that's all. Thank you very much.
Thank you very much, very interesting. And I think we can have, after all the presentation, some discussion, so we can come back with questions on your talk later. I have several questions for you, so be prepared. According to the program, now is Professor Zhuang.
Yes.
Okay, so he will talk about statistical seismology, point process, and Bayesian inversion. So
yes.
Please.
Okay, thank you. Thanks for inviting me to give a talk on statistical seismology, point process, Bayesian inversion method. I'm from the Institute of Statistical Mathematics. So what's the Institute of Statistical Mathematics? So we are a research institute built quite a long time ago, 8 years ago, even before within the Second World War. And we are basically doing something related to statistic control problem. And nowadays we belong to the, point here, belong to the Research Institute Organization of Information and Systems. So this is one of the Research Organization of Information and Systems is one of the inter-university research institutes of the Ministry of Education of Japan. So the objective of this institute is to research on statistical theory, methodology, and their application in the real-world problems. So it's founded in 1944. It's by the Ministry of Education, and then it's in 1950 it started Japanese National Tract Survey, and then in 1988 it became the Inter-University Research Institute. And so it is Inter-University Research Institute means it's a national research institute, but organized according to the universities. So in 1988, we joined the Graduate University for Advanced Studies, so we can teach PhD students and issue their degree certificate. And in the year of 2004, we become an independent research agency, one of the research organization of information and systems. And we moved to Tajigawa in 2007, before we located in downtown Tokyo. And in the year of 2010, we found the archaic guest house to help as accommodation service for international visitors. And then we are other things in the year. Now we are just reorganized for foundational research department. So here is our main activities, research activities. And we are almost the only research institute of statistical and mathematical science in Japan. And we are doing cutting-edge research. We have the network of excellence projects. And as Inter-University Research Institute, we do a lot of collaboration research program with diverse research fields. We have supercomputer system, software, everything. And we have also education programs. So we have 3 departments. One is advanced data science. We have the department interdisciplinary statistical mathematics. We have a department of fundamental statistical mathematics. And I'm from this department. So one important tool with our research institute is the network of excellence. So the aim of GILD is to build brand and new style collaboration research, and we have a synergistic effect from fusion of different fields. So we have 3 projects. Management of those kind of NOE projects is in our institute. So our research analysis research center where I moved from is one of the NOE network research center. We have different projects in different applicative areas for natural hazards. So we have also some education programs joined with the so-called Graduate University for Advanced Studies. The institute has a lot of international collaborations between with different research institutes around the world. This is OGS. We have just signed the MOU 2 years ago. So we have outreach in publication. We have 4 journals, AISM, the Annual Institute, Statistical Mathematics. We have Tokyo City, which is called the Proceedings of the Institute of Statistical Mathematics. And we have also some public relation journals, ISM News, and our annual report. And so come back to our research center. My research group is called Statistical Seismology. We are one of the research project one among the 7 research project, 6 research projects. We are doing earthquake probability forecasting, seismic network optimization, and probability earthquake early warning. So we have those are our members. We have members within our institute, and also the guest members from around the universities around Japan. And for statistical we focus on seismicity modeling and probability forecasting. So the ETAS model, which is now used a lot as a standard model for earthquake probability forecast, for probability shaking hazard assessment, it was created by the project leader of this our research group, Professor Yoshihiko Ogata. He's now retired, and I take over his position in charge of the research group. And we also have the task of detecting anomaly of seismic patterns. We estimate underground geophysical process through seismicity. And this is ETAS model. The ETAS model takes very simple assumptions it assumes we have in seismicity, we have background seismicity, which could be non-homogeneous. And also for earthquake clusters, each cluster will be triggered independently, but they have different size, different location time, different duration times, and spatial distribution, and almost different multi-stage. And then the cluster overlap with each other and with the background in space and in time. So this is the mathematical one of this one. And then this is Professor Ogata. And this figure shows a kind of how can we use ETAS model to do forecast or earthquake probability forecast. So this is 1 day before the 2003 Tokachi-Ochi earthquakes, and then this is the prediction part of the forecasting for on the day before the earthquake, and then this is on the day for the occurrence of the main shock, and then this is the forecasting of the aftershocks in different 2 days. And here we have the comparison between the observed earthquakes and the forecast after. It is quite variable, but both of them falls in the confidence bound. And nowadays our group is focusing on developing refined ETAS models. So we, starting from the original models, we focus on hierarchical models, trying to find how the classroom feature and background are related to the tectonic environment. And then we also develop a refined ETAS model, like the finite source ETAS model, in which we consider the geometry of the earthquake rupture. And also we have hypercentral ETAS model to think about the 3D ETAS model. And we also think ETAS model to incorporate focal mechanisms. And so this is, we are trying to develop more beta ETAS model. So this figure shows how the background seismicity are related to the focal mechanism. And this one shows how the ground shaking and the distribution of this direct triggered aftershocks. And this one showing how the focal mechanisms are correlated for the background seismicity and for the triggered earthquakes. And not all the earthquakes, we also do some risk analysis for crime data, use the HOX model. And we also do the geophysical inversion problems, which is a kind of geophysical geometry project with the institutes in China earthquake administration. Current project, we are working on a project from the Ministry of Education, MEXT, and which is called the New Development of Space-Time Earthquake Forecasting and Monitoring from long time to real time. So it is a joint project focused on static seismology, earthquake forecast, early warning, and network optimization with other institutes. So the first task of this one is to develop the advanced, to refine the ETAS model in which we're trying to improve the ETAS model from different aspects. And our domestic and international, this is our domestic and international collaborative network. We have the domestic ones, and we have the international ones, including the ISM and OGS. This is one with the Italy, and we also have the collaboration with INGV and IMATCNR. And recent and the current international collaborative includes those kind of funded research. We have the one with the China-Japan project. And this is the one we have also working with now we're working with New Zealand with project of forecasting future mega earthquakes on New Zealand, the largest fault, which is called the Hakurungi subduction ruins. And we also have some working with Australian University of New South Wales and New South Wales. And okay, thank you for listening. And we are our research group and our institute looking forward for further collaboration with Italian research institutes. Thank you.
Thank you, Professor Zhang. It was really also interesting also to see that you work also on Italian earthquakes. So our community is used to focus on different areas, not only locally. And following the last slide and the cooperation with Dr. Stefania Gentili, I give you the word for the presentation about, no, sorry, this is not your presentation. Yeah, about the international collaboration between OGS and the Institute of Statistical Seismology.
Well, thank you very much, and I will tell you something about the collaboration between us as OGS and the Institute of Statistical Mathematics. In particular, I will speak about a project we have in the years 2021-2023, and it is a bilateral project, and the Italian PI was me, while the Japanese PI was Professor Zhuang. So we have already a good collaboration that continued also after the end of the project. Well, if we speak of seismic hazard, we know that earthquakes are among the most common and costly natural hazards worldwide because they cause damages to structure, infrastructure, and they have also an important human cost because people dies. Unfortunately, it is still quite difficult. Also, if we heard a very interesting presentation from the previous speaker, to predict the location and the magnitude of earthquake. By now, we don't say something so strong, like to say, well, tomorrow in that town at 3 there will be a big earthquake. But one important thing to know about the seismic risk, it is that the risk, it is not only related with the main shock, so the main big earthquake, but also on what it follows the main shock. Because after a big earthquake, the buildings have been already damaged. So if a similar quake happens, it poses a significant threat from the civil protection point of view, because they can collapse due to a similar following earthquake. In many cluster of earthquakes that are all the earthquakes that follow the main one that are close in space and time, often we have the so-called aftershock. They are smaller magnitude earthquakes. Usually the magnitude it is 1.2 smaller. Consider that a magnitude 1 of difference is around 30 times the energy, so they are really smaller and so on. But we should consider that in some cases we have an earthquake, a following earthquake, that has magnitude of the order of the magnitude of the main shock, or even bigger if the main shock, it is not a main shock itself, but it is the so-called foreshock. So we can make some examples. For example, in Italy, in 2016, we had the Amatrice earthquake. Amatrice earthquake was a magnitude 6.0, but for Japan it is a smaller quake, but for Italy it is a very important one because we have about 300 deaths. But it was followed by a magnitude 6.5 2 months later. So this is a thing that should be considered. When we see a big earthquake, it may, we can consider a sort of operative main shock, but after another even stronger earthquake may happen. If we consider the very famous Tohoku earthquake of magnitude 9.1 in March 2011, we should consider also that it was preceded by a 7.2 event on 9 March. So if we consider the first one as the operative main shock, after the following one was really bigger and destructive. So the objective of the project we made together with the Institute of Statistical Mathematics of Tokyo, it is to develop practical techniques that helps us to estimate the probability to have a strong following earthquake. We analyzed the thing from 2 points of view. From the Italian side, together with another institute that it is to another institute, the INGV, we developed Nestore. Nestore means next strong related earthquake. It is a machine learning method that has been developed, and now the software is also available on GitHub, that subdivide the cluster, this group of earthquake that follow the operative main shock, so the first big earthquake, into 2 classes. If the difference in magnitude between the main shock and the strongest following earthquake is smaller than 1, we speak of type A clusters that are the most dangerous, while otherwise we speak of type B clusters. The idea of Nestore is to use the seismicity in the first hours or days after the main shock to forecast if the ongoing cluster will be of type A or of type B. So how dangerous it will be. From the Japanese point of view, as already told by Professor Zhuang, there is a big and long-lasting expertise on statistical seismology. The first pioneering studies were by Omori at the end of 19th century, 1894, who developed what it is well known in our field, that it is the so-called Omori law, that studied the frequency of earthquake in time. Toward the end of the 20th century, in 1998, Professor Ogata developed an improvement of his law, that it is the ETAS model, in which there may be more main shock, and so the seismicity can grow up again. And Professor Zhuang continues the work with also application of operational earthquake forecasting. So it was a great opportunity for us to collaborate with the Institute of Statistical Mathematics, of which both Professor Ogata and Professor Zhuang belong. So the idea, it was to use the statistical approach developed by the Institute of Statistical Mathematics together with a machine learning approach developed by us as OGS and by INGV, but it is another Italian institution. From the collaboration, we wanted to obtain a forecasting. During the project, we have organized several workshops, some hybrid and some in person, that allowed us to go, me, for example, to go in Japan, and people from the Japanese staff to come in Italy. For example, this is a meeting we have in November 2023. These are some results of the collaboration. These results I show you are the application of Nestore to both Italy and Japan. The first application on the left corresponded to the application of Italy. We analyzed the time intervals after the operative main shock, and here you can see in green the correct forecasting. It is important to say that they are retrospective forecasting. It means that we made after with the system that didn't know what will happen, and we compared what really have happened with the results of the system. You can see that there is a great majority of green dots that correspond to the position of the operative main shock of the cluster analyzed in time span on say 10 years, and here you can see that there is a great majority of green dots, so 86% are correctly forecasted by using the seismicity in the one day following the main shock. We also applied Nestore to Japan, and in this case we have that the 94% of the classification were correct by analyzing the first 6 hours after the main shock. Returning to Italy, you can see that the bottom, sorry, it is on the other side here, with bottom yellow dot, that forced us to study in more detail that cluster. And that allowed us to make other work in collaboration together with ISM and OGS. This is a cluster happened in Italy in 2018, and it was characterized by the abrupt interruption of seismicity. There was a first part of the cluster in April 2018, and in the same place collocated, we had another increase of seismicity in August, and in the middle we didn't have anything. We studied this in more detail by a new method of template matching that was developed thanks to the collaboration with the Professor Kato of the University of Tokyo something like 10 years ago. And thanks to this more detailed data, we were able to study the seismicity also in the this first part of the cluster, and we discovered that there were a lot of anomalies that made our think that it was one only cluster, and to hypothesize that the fluid pressure variation caused these relative equations that was studied by Professor Zhuang by using the ETAS method between the April and the August seismicity, and so caused the stop of seismicity that, and when the August events of higher energy happened, the fluid are released, and we have a migration of seismicity according to the movement of a fluid. So it was a good work, a very interesting work, because it was done in collaboration between many different expertise. going on. This is another result we obtained together with Professor Zhuang on the integration of different catalogs in terms of magnitude, because different catalogs often use different magnitude or different estimation of the same magnitude. So it is a statistical approach that can merge together also different catalogs. And the other results regard the cluster identification, automatic cluster identification, that was particularly challenging in case of the on the Japan seismicity, that it is extremely complex. And we also use we use the ETAS, and we use also the graph theory. So it was an interesting results. Our results of the project were presented to a huge number of congresses, of scientific congresses, and was published on a lot of publications. And the press communication. We had several visits and a presentation in Congress around the world. And here is a meeting we had in Tokyo at the ISM. At ISM, where we had a collaboration between Professor Zhuang and me, and also the attaché on the embassy, Professor Traversa, came there, and also there was a Professor Tsubaki, that was the general director of ISM, and well, there is also Dr. Petrillo that collaborated with the Japanese staff. This was important because allowed us to make a memorandum of understanding between the two institutes, and so to continue also the collaboration in the following years. These are some examples of the work we are still doing together about catalog merging and cluster identification. And these are the projects that found the research. First of all, the already mentioned bilateral project between Italy and Japan, and but also the PNRR return, that it is funded by the European Union, that in which we continued our analysis, and the project Nemesis, that was a project is a project of INGV, and that has as external participant both Professor Zhuang, me, and Dr. Brondi, who works at the OGS like me. So thank you for your attention.
Thank you very much, Stefania. I think this is a nice example of cooperation between our countries, and I hope that meetings like also what we are doing today can help in future to strengthen and further develop the cooperation among us, because only through the exchange of ideas and the exchange of experience we can advance in our knowledge. So now is the turn of Professor Kato, and he will tell us something about the long persisting seismic swarm and the subsequent nucleation of the 2024 magnitude 7.6 Noto earthquake. Thank you.
Thank you very much for a great introduction, and I greatly appreciate inviting me to give here. Thank you very much. And I'm Aito Kato from the Earthquake Research Institute, the University of Tokyo. So my talk is focused on the seismic swarm activities that has occurred in the Noto Peninsula in Japan. And previous talks give us more wider perspective, but I stick to the one event. And so this is a photograph taken in the port in the Noto region. So in this earthquake occurred in 2024, January 1st. So that is timing was a Happy New Year, and the evening of the January 1st, and it causes a significant destructive damage along the northern coast of Noto Peninsula. So this is one of the port which was uplifted during this earthquake. So you can see that this amount. So this is sorry. So this is so this is a 4 meter height. So this is our sea levels before the earthquakes. Okay, so after the earthquake, so this port was uplifted. So this is my student. So he's standing. So he's less than 2 meters. So you can see that. So this uplift occurred during this 2024 magnitude 7.6 earthquakes in Noto Peninsula. So, but before this big event, with a long persisting seismic activity, so we call that is a seismic swarm activity. So Stephanie has already mentioned about such activity in Italy also. You have such a long lasting earthquake swarm associated with the big earthquakes. So it's very similar. So as so just a brief introduction, I will show you some tectonic summary in Japanese island. So we are now here in Osaka here. So along the Japanese island, the 2 oceanic plates is subducting. So one is the Pacific plate is subducting from east to the west side, and the other one is the Philippine Sea plate is subducting the north westward. So the Japanese island is sandwiched by the convergence of the 2 plates. Noto area is located here, so it is a Noto Peninsula at the eastern. So this is the Japan Sea. So Noto Peninsula is located at the eastern margin of the Japan Sea. So along the eastern margin of the Japan Sea, there's a very big deformation occurred in the past. So from the 1,050 million years ago, so along the Japan Sea, so Japanese Sea was created actually. So Japanese island was actually connected or part of the Eurasian plate. So here, so Japanese island is located here actually, in the very old time. But so 15,000 million years ago, 15 million years ago, Japanese island is extended and moving towards the southward. So we had a Japan Sea here. So during this extensional stage, there are many faults that created by the extensional stress regime. Then 3 million years ago to the present, the compressive stress regime has been dominant. So now we have many reverse faulting through the tectonic inversion framework. Okay, so we have many fault structure along the eastern margin of the Japan Sea. So this is a time series of the magnitude associated with this node earthquake sequence. So this is the magnitude, and this is the time from the 2022 up to the end of the 2023. So you can see that so this is a red curve showing the cumulative number of the earthquakes associated with this storm activity. So the gradually number of the earthquakes gradually increases, and we had a magnitude 5 or 6.5 earthquakes during 3 years seismic storm sequence. Then we had a magnitude 6. During this time, we have observed a clear cluster deformation associated with this storm activity. So you can see that this kind of the pattern of the surface deformation. So you can see such kind of radiative pattern of the surface deformation, which related to the fluid migration from the deeper parts to the shallow depths. So this bottom panel showing some cartoon showing the deformation associated with the earthquake storm activity. So the fluid is coming up to the shallow depths, and then it causes some slow slip. So slow slip is a slow motion of the fault movement, and it causes a seismic storm sequence during this stage. Okay. So we can also see the clear long-term migration of seismicity associated with this storm activity. So for example, this is the depth of the versus time. you can see the clear shallowing of the seismicity from the deeper part to the shallow depths. Okay, so right panel is also shown is a color code is a time. So from the beginning of this storm activity, you can see the systematic shallowing of the seismicity associated with this activity. So this also implies a fluid is coming to the deeper depths, and it causes a shallow seismicities, and it also causes a long-lasting earthquake activity in the shallow cluster depths. And we also find the more rapid shallowings of earthquake activity associated with the magnitude, for example, 6.5 earthquakes. So you can see this is a depth. Oh, sorry. So this is the depth of the time after the magnitude 6.5 earthquake. You can see the rapid expansion of the aftershocks region. So this is a very rapid. So the front migration speed is 20 km/h. So that is the same as the speed of the bicycle. Okay, so it's very rapid migration. So we interpret that is caused by rapid fluid migration after the magnitude 6.5 earthquakes, because the earthquake occurred, then we had many fractures associated with the earthquake. So there are many spaces for fluid to migrate. So we interpret this rapid earthquake aftershock expansion could be driven by the fluid migration. So then after the 3 years earthquake swarm activity, we had a magnitude 6.7 destructive earthquakes. So it causes a very severe damage along the northern coast of the Noto Peninsula, and as shown by these pictures. Okay. And so this is go back to the magnitude and time series. So, So this is after the magnitude 6.5 earthquake. We have still high activity of the seismicity. So we have a magnitude 6.0 earthquakes in the swarm region, and in last November we had a magnitude 6.6 earthquakes in the western part of the Noto earthquake region. So the bottom panel is showing the epicenter distribution of the seismicity. So before the magnitude 7.6 rupture, they are concentrated in the northern tip of the Noto Peninsula. But after this biggest event, the aftershock zone is extending to the northeast to the southwestward. So this is length is more than 150 kilometers. So it's very widening. And this, there are several studies about the rupture process of this magnitude 7.6 earthquake. So these studies suggest earthquake rupture is very complex because these earthquakes expanded from this previous region to the southwestward and northeastward, and rupturing the multiple different fault segments during this earthquake. So actually the duration of this earthquake is less than 2 minutes, but earthquakes started in this preceding storm region and expanding to the along the fault strikes, and it causes multiple ruptures of different faults. And so this is something like relocated seismicity associated with storm activity. So before magnitude 7.6 earthquakes. So this is so the seismicity is very concentrated in the northern tip of the Noto Peninsula, and this is the cross section of each slices. You can see the southeast dipping clear alignments of these seismicity. So it means that there are several faults dipping to the southeastward, and they are activated during this seismic storm period, and those seismicity may be driven by the fluid migration, as I explained before. And after 7.6 earthquake, so you can see the change of the seismic pattern, like this one. So seismicities are the center of seismicity getting more shallower part, and you can see the more continuous distribution of the aftershock from the surface to the more deeper depths. But they're also showing a similar southeast dipping fault. So this is the before, and this is the after the magnitude 7.6 earthquakes. Okay, so still the southeast dipping structures are dominant, and this southeast dominant structure was created during the opening of the Japan Sea, as I mentioned before in the introduction. Okay, so, and I focus on some immediate seismicity before the magnitude 6.7 earthquakes. And so this is the time versus epicenter distance along the fault strike. You can, so this is some storm activities that was lasted so during the 3 years. And then you can see some concentration of the some seismicity just before the magnitude 7.6 earthquakes. So they are occurred in the map scale here. So this is a blue star is the epicenter of the magnitude 7.6 earthquake. So northwestern side of this main shock epicenter, we have some immediate shock activity. They are very active right before the 4 minutes, less than 10 minutes. Less than 10 minutes. But if you look at more precisely here, then this seismicity actually occurring in the 1.5 hours before the main shock rupture. So this some tiny cluster activity started around here. Then we have the magnitude 5.5 or largest one is the 5.9 earthquakes. That is a final foreshocks before the main shock activity, main shock rupture. Okay. So this is okay. So this is a cartoon showing the summary of this sequence. So before magnitude 7.6 largest earthquakes. As I mentioned before, the storm activity occurs by the fluid driven, maybe fluid driven seismicity, and it causes the slow slips. And this slow slip causes a stress loading onto the shallow depths, and this stress concentration bring out the storm activity for 3 years. Then we have a magnitude 6.5 earthquake occurs, and maybe fluid is propagated or migrated to the shallow depths. Then we have the magnitude 7.6 event ruptures. Then they are slightly shallower depths and connect to the active fault traces on the sea floor. So this is a main trend associated with the magnitude 7.6 event. And before this largest event, we have a foreshocks, but they occurred at the different fault systems at more deeper depths, and they are almost coincide with the rupture plane associated with the magnitude 6.5 event in 2023 event. Okay, so yeah, so that is my summary. So yeah, another earthquake sequence is very complex. So we had 3 years seismic storm activity, and still seismicity is yes, they show some fluctuation actually, but it's still continued. Then after that, we had the magnitude 7.6 largest event. So yeah, right before we have some activities, so like foreshocks activities, but yeah, it's very light, very just immediate. So it's still challenging to forecast seismicity more precisely based on. So we need to more study to do that. Okay. Thank you very much for your attention.
Yes, thank you. Really interesting. And again, there is a connection, like you highlighted, with the L'Aquila earthquake and the role of crustal fluids. So I think that the experimental observation in Italy and Japan can really teach us something about the generation process. So now is the turn of Professor Bogdan Enescu. Yes, with it should be on. Ah, yes. Okay.
Okay.
He is going to present us an integrated relocation workflow for offshore earthquake sequences,
Okay.
and yeah, with application in Italy and Japan.
Okay.
Here, if you like, there is some water.
Some water,
So
okay.
Feel free to to have.
Thank you, Matteo and Stefania and everyone for organizing this event. I'm very glad to be here. I'm Bogdan Enescu from which one is the
This is the point.
Yeah, I'm from the Department of Geophysics, Graduate School of Science, Kyoto University. And I will present just a few slides. I didn't prepare much. So this is an example of collaborative research we've done recently. And the research was led by one of our students who graduated recently, Lai An, from China. In a really international team. So this is part of two studies, one published already and another one in preparation. So applications to Italy and Japan. So one of the basic problems in when we deal with earthquakes is to locate them. It's a basic activity. However, for offshore seismicity, sometimes or many times the location of earthquakes it's challenging. So it's difficult to locate earthquakes far offshore, in particular. And this is because we don't have stations surrounding that area. So it's a basic thing. We need all seismologists work with hypocenters, or most of them. So it's very important to have high resolution imaging of this seismogenic structure for offshore earthquakes. Yeah, they are a basic foundation for better hazard models, for example. So essentially, this is what I already said. Well, we do have recently, Japan is a very good example, Italy as well, where the deployment of ocean bottom seismometers, or OBS, can improve the characterization of offshore seismic sequences, but sometimes they are noisy, are significantly costly, and they are not available everywhere, and especially they are not available for old data. Yeah. So then, so that's why ongoing research efforts, what we actually did as well in this study, are focused on refining existing technologies and developing new solutions for detecting and locating earthquakes, in particular those that happen offshore. In order to tackle the location of earthquakes with insufficient station coverage, there are various approaches that have been proposed in the literature. Probably one of them, one of the first, that is one of by Sarr in 1991, another one by Abercrombie in 1995. However, still the network sequences, the offshore network sequences, their location remains challenging. And new methodologies, workflows taking advantage of new developments and new big data availability are also highly demanded. So the relocation workflow that we have here proposed is essentially based on several, I think 3 or 4 different methods that were developed in previous research. And here comes the collaboration with our Italian colleagues. I'm sorry, I want to return to this first slide. So Professor Grigoli from the University of Pisa, with whom I am collaborating frequently in the last maybe 5-10 years, and of course other colleagues from Italy and Japan. So in collaboration, we did that study. And so the method, the relocation workflow that was proposed consists in several steps. First, the workflow locates reference or master events. I will not go now into details about the full methodology. We do absolute locations using a number of 3+ stations. And we implemented a very careful depth phase analysis for earthquake depth determination. So for offshore earthquakes, for earthquakes that occur far from the shore, one challenge is to determine precisely the depths of those earthquakes. The depth is actually the most critical or less well-constrained parameter. But by doing depth phase analysis, one could really improve this depth determination. And again, it's not the purpose of this presentation, but we improved previous research. We looked at earthquake in order to discriminate between different types of depth phases. We looked at the radiation pattern and different other informations. And after we do these 2 steps, we reconstruct, we apply a method proposed by Professor Grigoli to reconstruct the earthquake cluster geometry. This method was used before in biochemistry, actually, where they want to locate some molecules depending on the location of other molecules. So, and the method is very good, especially when you have a few stations, only a few stations available, and located somehow far away from your earthquake cluster. It's a relative location method, and at this step, at this level of research now, we use 2 stations. We plan to extend this method because sometimes there are more than 2 stations available, maybe 3 or 4. But already the results that we obtained so far are promising. So we also published some of these results. And finally, we do result validation, visualization, and cross-reference. So this is the first example. We have applied this workflow approach to a relatively recent earthquake that happened in 2002 in the northern Adriatic Sea. Yeah, so this is the location of the main shock and following aftershocks. The data being provided by the National Institute of Geophysics and Volcanology, in Italian the Istituto Nazionale di Geofisica e Vulcanologia, with whom some of the researchers in my first slide were from this Italian institute, with whom we also collaborate. So by doing this workflow, we could successfully reconstruct the earthquake cluster. So these are the on the map in the A part of this figure. You see the earthquakes with circles. Yeah, the size of these circles scales with the magnitude of the earthquake, while the colors show the depths, right? And this is the A map. And in B and C, there are cross sections along this earthquake distribution. And you can see a quite good reconstruction. I'm not going to tell you all the symbols, what they mean now, but you can see that, there is a clear, so for a profile oriented from A to A prime and the other one from B to B prime, you can see the seismicity becomes clustered and well aligned with the structure, with the geologic structure there. we did some result comparison. The blue dots are our location results. The red dots are the initial catalog locations. And overall, our distribution aligns better, I think, especially that we use only 2 stations for the cluster for the cluster geometry. So you can see the earthquakes appeared well clustered, and they define these faulting structures over there. And well, in geophysical research, many people, including some who are here, for example, Professor Kato, we are all familiar with this HypoDD method. So you can see a comparison between HypoDD that uses much more stations, actually 55 stations, and our result that uses only 2 stations. The clusters are for different time periods, so we focused, so our result shown in the right, focuses only at the beginning of the sequence, while the Italian catalog includes a much longer period, a longer time period. So anyway, from the cross sections in the middle, AA prime and AA prime, our result, you can see that the 2 results are comparable and they are showing practically the same fault structure. So of course, the method, as we discuss and as Lai Kan-san discusses in his thesis, there are still some problems with the robustness of the method, but I believe is a very promising, approach for critical conditions when you have very few stations available and somehow your earthquakes are located offshore. And finally, we applied the same. This is our paper in preparation. We applied the same workflow to Hachijojima sequence. This is an offshore, far offshore earthquake sequence that happened in 2023. We implemented this a very careful depth phase analysis, and I'm not again showing the details, but you can see in the waveforms there are some P wave arrivals, so the phase of the P and also the SP. And we improved in such way, using depth phases, we improved the depths of the reference events. Yeah, so this was the second step of our location workflow. And again, this is a result comparison using the blue dots are our result based on reference events that are located by us and depths corrected by depth phases. The yellow dots are our result with reference events based on the GMA catalog. And finally, the red dots are the GMA catalog locations. For those who are not familiar, GMA is the Japan Meteorological Agency. Professor Hoshiba is from GMA. So using these techniques, we determine a much shallower cluster. Yeah, so you see the blue dots here are going to shallow depths, which is consistent with this volcanic, with rather shallow swarm-like cluster. Yeah, so we believe that the location function of depths, it's better constrained. Yeah, and overall, again, the cluster geometry shows similar features with the GMA catalog locations, but again, the seismicity gets shallower, and probably we have a much better defined cluster of events. So again, in conclusion, we provided a workflow that is able to have to give a first order approximation of offshore cluster geometry, only using 2 seismic stations. We applied this for a recent sequence in Adriatic in 2022, and for another one in Hachijojima. Yeah. And our results are in good agreement with the structure, with the the geologic structure and other earthquake parameters. well, despite this overall reasonable performance of our workflow, there is some variability of earthquake location solutions, especially concerning the relative location method. So now, Lai Kansan, who will be a postdoc in Hokkaido from June, probably will work to further improve this methodology. And that's all. Thank you for your attention. Just here are just one moment, because I actually this is some example of other collaborative work with Italian, Swiss, and Romanian colleagues. For example, a recent paper by Gulia et al., where we use the so-called four-shock traffic light system based on B values. A specialty of probably next speaker is working a lot on B values. And I'm originally from Romania, yeah. I'm for almost 30 years, or 26 years actually, in Japan. So I still work a lot with colleagues from Romania. That's another example from Romania. So that's all. Thank you.
Thank you very much, Bogdan, for this other example of cooperative work. And I think the strategy is really interesting, also thinking to monitoring of induced seismicity related, for instance, to the carbon capture and storage that is done in Adriatic Sea. So this is exactly the kind of problem that we could have with a few stations on the coast. So it's really interesting. So now is the turn of Professor Nanjo, and he's going to speak about the tower detecting anomalies that differ from ordinary seismic and geodetic patterns, possible direction for future joint initiatives.
Thank you very much. And thank you very much for inviting me for this conference. And I'm very happy to be here. And my name is Kazu Nanjo from University of Shizuoka. And so today I will talk about some idea of the research that might be related with possible directions for the future joint initiatives. Okay, so before going to details, I briefly explain my university and myself. And my university, it's a University of Shizuoka, is located in the Shizuoka Prefecture at the center of Japan, and it takes 1 hour from Tokyo by using the Shinkansen Super Express. And Shizuoka is famous for, maybe everybody knows, Mount Fuji. And it's the highest mountain in Japan, and 4 kilometers height above sea level. And so from my university, so we can see beautiful Mount Fuji here. And then next, I will explain myself. And my research interest is earth science, including earthquakes, volcanoes, and natural disasters. So sometimes I use computers very intensively, but sometimes I go to field survey to install some seismometers or any single instrument. So I have to do anything because my institute, my section is very small, only 2 people, so that's why I have to work many kinds of stuff. So actually, I was suggested to give some topics related with the 3 points. And so this is a proposal from the organizers. So one is a past activity for the collaboration, but the other one, the second one is a possible direction for future joint initiatives. And the third one is the emergence trend in seismology. And I was thinking, but maybe I can give some talks related with 2 and 3. So I want to give some idea of the research for the future directions. And this might be a good point. So for the future joint collaboration, Italy and Japan. So that's why I proposed one idea. And maybe finally, so this might be important for the societies or local communities. So I want to discuss more about you Italian people. So I want to give you some small introduction about Japan, but Kato-san have already done about the Japan seismic setting and the technical setting. So once again, so Japan is very active area of seismicity. So because of high seismicity, so Japan government published seismic hazard assessment. So these are maps of plate boundaries and active fault with the information of the occurrence probability for 30 years and expected magnitude. For example, so Hinagu fault zone, so in the Kyushu area, has information on the magnitude of 7 class and high probability colored in red. So, this one. So this is the Hinagu fault, and then so this is the Japanese, but this is the English one. So Hinagu fault is located here at the center of the Kyushu Island. Okay. So this information is very important for the seismic hazard assessment. However, we feel need to more about research contributing to the in-depth seismic hazard assessment because Kumamoto earthquake occurred about 10 years ago along the northern Hinagu fault zone and adjacent Futagawa fault zone. So future seismicity is a serious concern, especially for the local people and the local communities. So if science and technologies are available for detecting some anomalies that differ from the ordinary seismic patterns, this might give us some clues of possible scenarios that likely happen in future. So I will give us some brief summary of such research done by our group, especially for the Kumamoto earthquake sequence. So I briefly introduce Kumamoto earthquake, and the main shock is a magnitude of 7.3 earthquake, April 16, 2016, along the Futagawa fault. So I mean the red line. And there is a unique characteristic, namely foreshocks occurred in, along northern Hinagu fault zone. It's a blue line. Okay, I will skip, and then so by default, we know the main shock occurred on the Futagawa fault, and the foreshock occurred Hinagu fault, especially northern part of the Hinagu fault. So from here on, so we studied about the geodetic data and analyzed parameters such as B-value characterizing frequency magnitude distribution and aftershock decay showing the decreasing seismicity that followed the main shock, and aftershock model showing the post-earthquake motion along causative faults. So, and then so in this talk, so I will show the summary of the results, but I don't show so much about the details. So I will give some small, like a summary, and then especially I will focus on the slip conditions along faults. So. And then so our results found such a some kind of the information, and I finally wrote some cartoon that express our results. And then so first along black segments. So sleep occurs due to the after sleep. It's a slow motion along the fault zone after the main shock and for shocks. And along white segment, it's a southern part. So white part, white segment. So no sleep occurred. And gray segment. So this shows the transition between the sleep and the no sleep. So central Hinang fault zone was interpreted as a locked area where the stress is high. So to show stress was really high at central Hinang fault zone, we show one result based on the B value parameter reflecting the stress state. So low B implies the high stress. So time series shows the B value decreases after the Kumamoto earthquake, implying high stress. And we can see two colors here. So it's just a change of the boundary conditions. And we can see some similar pattern. It's a high, low B value, which means a high stress. Further, we recently conducted follow-up exam showing the B value, and we show the B value was still low. We have a concern about high stress area because some examples from Japan and California and other regions revealed that rupture initiation started from the high stress area. So our concern was one scenario that the future rupture would nucleate at central Hinang fault zone and propagate to the unruptured southern section colored in white. So we think this is a case detecting anomalies based on the geophysical data. So science and technology available for detecting anomalies, as shown here, may help image scenarios of how earthquake likely happens in future. So I emphasize our result is not an alternative to the seismic, government seismic hazard assessment, but adds some information that may be taken into consideration. So our group thought local community and residents need to know what happened in Kumamoto and scenarios of how earthquake possibly happened in future. So I visited Kumamoto Prefecture to conduct press release. I also proposed this scenario can be used for disaster mitigation to, for example, encouraging local community and residents to reconfirm earthquake preparedness on a daily basis. So far, actually, so no earthquake occurred. So we checked B value again using most recent data until the end of the March of this year, and it seems B is still low at the central part of Hinang fault. This part still low. So it means that the high stress area. So monitoring of Hinang fault zone is important to understand how anomaly changed or remains unchanged. So once again, our study may help image possible scenarios of how earthquake possibly happened in future. So our implication is that such scenario may be basic information to help prioritize drills for emergency management. Of course, any drills are possible, assuming any scenarios, but local government and residents may prefer conducting drills for emergency management, assuming scenarios based on scholarly data like the one we discussed here. So this is the last slide. And so today I brought some idea which might be collaborate with you. And then so I think this might be good point to be considered for the emergency management or something like that. So this is all my talk. Thank you very much.
Thank you very much, and I think this is a perfect step for the discussion. You raised a very interesting issue that can be covered. I have a few questions for all of you, and I took a note also of some topics. First of all, I have a question concerning a few questions concerning the early warning part. So, which is really the operative way to mitigate the risk, where you are a long-standing experience. Now, in Europe or worldwide, we are facing a new revolution, that is the revolution of artificial intelligence. And how do you think this will impact the early warning activities? And in Italy, we have a serious concern after the L'Aquila 2009 earthquake and the trial that was posed against the civil protection and the scientists because they didn't forecast the earthquake. So, do you think that artificial intelligence approaches are useful, and is there any legal issue related to the failure of a method based on artificial intelligence? Because
so yeah, AI is they have a potential for improving the ASCII early warning. So one is, what I'm concerned is, it's a lot of earthquake is small event. So we don't have so much large event. So ASCII early warning should be effective during large earthquake. Small earthquake is no important on ASCII early warning. So one is important is we need a lot of data from the large earthquake for AI promotions. So AI is very powerful, but we need also observation, actual observations. And also from a viewpoint of the force around by AI. So it's one of the important things we can explain general public why we fail. So one way is at present, I think the AI, we don't know how AI, how decide these decisions. So one of the important thing for future for applying ASCII early warning, you have to explain why AI failed or yeah, something like that. So that is we have a responsibility for explanation for general public. So that is one of the important things for AI for implementation using AI.
Okay, thank you very much. And another question, this is important, it's really interesting also the different awareness of people about seismic risk. So it seems that here the people is accepting that the early warning can fail time to time. And in Italy, after that earthquake, after the L'Aquila earthquake, is a little bit more difficult to deal with the public release of alert. Indeed, we are not yet well advanced in this topic. So what we develop scientifically is not immediately put in operation. We are still with some delay, let's say. And I think this was something related to that earthquake. And we have seen here many interesting aspects related to the physics of the earthquake generation and also related to the operational forecasting. Are you try to implement the operational forecasting also in Japan, or already you have done it?
You mean is a prediction?
Yes. Yes. So you are active with early warning, and we have seen here, we have the community of people working with statistical seismology and developing operational earthquake forecasting. Is there a plan to implement in real time also this kind of tool to mitigate the risk?
So that is depending on how precise we can do. It's one of the important things. Because so for example, it's at the present with our prediction is it's a percentage, not 1-0 decisions. That's a percentage. So percentage is not so acceptable for general public. Okay. So probability expression is not so good for the general public. So people don't understand probability. So one of the important things to implement with prediction something is how reliable we are for accepting by people.
Okay, maybe we can ask people.
Okay, I have some discussion with Matteo's question about the OEF, operational earthquake forecast. So basically in Japan, we are still thinking about to develop operational earthquake forecast. People in Japan have already quite tolerated to run forecasting, one prediction, something like that. But this is still quite a serious problem in China, in Italy as well. People will say the authorities should give us something like precise information. But OEF saying, no, we cannot give you the precise information. We can give you the information with uncertainty. Just for example, if you go out today with a 1/1,000,000 probability to have a traffic accident, so will you like to go out to do your things, or just you hide in your house doing nothing? So this you make a decision. So we know that kind of low probability will happen to everyone for traffic accident. But once we say, for like earthquake probability, we say, okay, usual probability is 1/1,000,000 you have this accident. But today will be quite dangerous. It's something like 1/10,000, 100 times higher than that. So are you still thinking about it's necessary to you to stay in the house or to go outside to your business? So of course, if you have very important thing to do, you say, okay, I will go out to do my thing, but with to be slightly careful of those kind of traffic accident or earthquake, something else. So this is a way. So OEF more like kind of advice than something, not a kind of a kind of power to force you not to do something, to do something. So this is the idea about OEF. I think this also the proper way to trade with probability forecast. So everything, forecast is the most difficult thing in the world, in fact.
Thank you. Bogdan, you also work on this topic, maybe.
Yeah, so I think among earthquakes, aftershocks are probably the ones that we know well that, after a large earthquake, a main shock, they decay in a certain way. And probabilistic models for aftershocks are well developed. So I believe that I believe in aftershock forecasting because, as someone said, at relatively short time after a large earthquake, you can have a large aftershock that can, destroy the buildings that were already made kind of weak by the main shock. Yeah. But again, there is a question that I cannot decide. I'm not here to decide, but I don't know whether, informing the public about that would be really useful or not. Somehow, on one side, I think it is useful, but it also depends on every person in part, whether, maybe you are scared a lot about, such a forecast. And if you hear many times a forecast, you are not going to be happy about that, you know. It's not a certainty. You don't have a certainty. So dealing with these things is very delicate. So this is about aftershocks. Now about just regular seismicity, it's much more difficult. There are systems in use based on B values, for example, that Nanjo-san, Professor Nanjo described previously. There are systems in use, and they are actually working in real time or quasi-real time. There is such a system developed by Italian colleagues, by ETH colleagues, where we also participate. And it shows some interesting results, but I believe they are more interesting still for the scientific community than for the public. So how this will move to the public and in what way it can be useful for the public, it's an open subject, I believe. But gradually, I think, you know, more and more we will introduce, and probably GMA might introduce one day in the future, this kind of forecasting if it becomes more reliable. Yeah, I believe this time will come.
This is the direction.
Yeah, this might be the direction, probably. Yeah.
I think that in Italy, where we have the same kind of problem, maybe slowly the people awareness is changing related to the forecasting of extreme event related to climate. Since they are becoming more and more frequent, the people is accepting that there is the idea of forecasting and of a probability associated to these forecasts. And probably sometimes they will be educated about this kind of hazard, and the same experience can be translated to earthquakes, where of course is much more difficult. But if the people is aware about the probability concept, probably in future they could use this information.
Yeah, from the education of people, when, just before an introduction of the earthquake warning by GMA, so GMA conducted a quite big campaign for education of people. So because it's we are researchers and technical viewpoint, but it's education of people is also quite important for actual applications. So yeah, we are researchers, so we can usually discuss with a seismological viewpoint. But from viewpoint of general public, so it is important to approaching to each other to effective information. So we are good information is helpful. We believe it, but people don't understand it. No meaning. So that's what education of the people is very important in addition to technology development.
I totally agree.
Yeah, I agree. Yeah, education is very important. So, but yeah, in terms of earthquake forecasting, yeah, as you mentioned that yeah, we have a very large uncertainties for the forecasting. So yeah, Bogdan said that for us, aftershocks forecasting is more easier, but it depends on the case. So yeah, it depends on the case, I think so. But so we need to still study. So what's the difference of that? Yeah, maybe Stephanie already presented the class A, class B sequence discrimination. So it's one way, but we need more time to verify the results and our algorithm. So, but still, yeah, we have some large uncertainties, and Johansson said the probabilities are very low for big earthquakes. So relatively, we can say some relative change of the probability with time. So if it's some bigger seismic storm or some earthquake occur, then we have some sharp increase, a relative increase of probability. But the absolute probability is still low, so it's not acceptable for the public people. So the public people cannot do anything to prepare for the potential big earthquake. So yeah, so education is very important, but yeah, we need to study to output more accurate and precision. So with the low uncertainties, information is very important to move the public.
I fully agree. Well, what I meant to say, for example, as Kato-san knows, NID has a system to forecast that is, you know, a real-time system. Yes. And they make available those results internally, sometimes communicating at meetings. Yeah. I know Zhuang-san and Nanjo-san also work on similar things, but NID has a kind of, you know, they are kind of not official, but more or less more official internal institution. So there are such systems, but I agree with you that we are still not able to provide some, you know, black and white forecasts. The uncertainties are large. But still, I believe these efforts one day, I'm optimistic, so I believe.
I understand, of course. But discrimination is not so clear. So you said white and black.
It's still challenging.
It's still challenging. So because society needs a white and black decision. So that is a very big, but we have a big large uncertainty.
So I have a question related to the L'Aquila Trail. You know, it is a problem happens with the civil protection and INGV. So it seems the OGS have similar functions as INGV. So I just trying to know whether it is some similar case, similar possibility will happen to OGS.
While that was a special condition where the communication was not properly done to the public in that period of stress. And at the end of the complete trial, only one people, which was the vice director of the civil protection, was convicted. All the others at the end were released by any problem. That created some problem in our community, and at the same time, if we want to see the good issue, it really learned us that it's really important to communicate in the proper way, and it is really important not provide information, let's say, that make everything easy. So we have to inform the people that the hazard in some region is high, and that they must somehow be prepared to an earthquake. So generally, during seismic crisis, now we communicate also the operational forecasting information to the civil protection, everything that we do to the civil protection. And the civil protection developed a lot of expertise to communicate with the people this information. This was an experience that taught us how to behave correctly, and it's important. And I have seen interesting studies that you have presented, also concerning the change of parameters related to few large earthquakes. More or less we also do, and also other colleagues worldwide are doing. And in Europe, and related to this EPOS project, we are developing the idea to create near-fault observatories, which are places where we also combine different expertises, trying to combine also people and studies from geochemistry, from geodesy, seismology. Do you have some similar plan here in Japan? Are you doing similar cooperative efforts to study K faults? For instance, in Italy, we have 3 near-fault observatories. One in the Irpinia area, where there was the 1980 magnitude 7 earthquake. One in Valtiberina, which is central Italy, and one at northeastern Italy, so is where we work, related to the 1976 earthquake. So these 3 areas have been selected to have some extra effort of our community, but not only seismologists, to try to understand the preparatory phase of large earthquake. Do you have something similar? Do you think it could be interesting to create some international group of near-fault observatories also
It's
between
very
Italy and Japan.
Great idea. I think it's very good. So it's promising. So, how many stations or how many equipment do you install at each site? Or
Let's say that
Yeah.
in our site
Yeah.
we have 40 velocimeter around the epicentral area of the 1976, and then we have many hundreds of accelerometers in the regions. But for studying the microseismicity, we use just a few tens of velocimeters, which are enough for the detection of low magnitude earthquakes and their location. And now we are going to set up also geochemistry stations to study the emission of CO2, for instance, or other, since we understood that fluids, crustal fluids are important in some area, we are trying to include also the geochemistry in this kind of observatory, and of course the deformation. And maybe also time to time we do survey with the gravimetry to see if there are also changes in the long term. So we are trying to develop this concept that to study the preparatory phase we should combine a large community.
Yeah, and in Japan, recently we don't have such a project, especially to the near fault observatory. But we have Hoshiba-san showed us we have many seismic stations already around, and now we have offshore seismometer is already deployed along the Pacific side. So so we can increase more, increase density, adding the more stations or through the collaboration with the different fields, such kinds of the geochemical researchers. But currently we don't have such a project now.
About 20 years ago, the Italy Shizuoka lines, there's some project. But at present, not so much activity. So 20 years ago, we had such kind of, we had. But at the present, so I don't know so much.
So I have one topic related with this, because recently, so our group started monitoring of the Southern Alps in the Shizuoka prefecture, in the northern part of Shizuoka, because this area is very important because Maglev Shinkansen, so it's a very, very fast Shinkansen, will go through the Southern Alps, and then so Shinkansen need to tunnel under the Southern Alps. And we are worried about this Shinkansen because underground water goes out from the, because of the tunnels. So that's why, so we are very worried about this point. So that's why Shizuoka prefecture, especially for our group, started to monitor the cluster movement. One is a seismometer, earthquakes, microseismicity. The other one is geodetic deformations, like landslides. And also we try to measure the chemical component of the underground water. And also we want to collaborate with biological people because we want to know the biological some stuff within the water, because we are very worried about the change before and after the digging hot tunnel. So that's why we have to know, we have to monitor before the starting of the digging fault. And then after the digging fault, I mean the tunnel, so we have to monitor again because we want to compare between these two situations. So now we are now collaborating with several people, like geophysics, like me, and the geochemistry, and also geology, and also I want to include the biological people. So this is kind of, but this location is very, very limited. So that's why it's a very small community. But still, we can need to monitor. We have to need a collaboration, such as specific situations. So maybe this is one of the example, but it's very specific situations.
Yeah, but the idea of these near fault observatories, so you have seen that in Italy we have also a large number of seismic stations. So the general monitoring is excellent. But the idea was to create some natural laboratory. So as a seismologist, unfortunately, we cannot play in laboratory with fault. It's not so easy. Maybe from the mechanic point of view, people working with sample are doing similar things. But we don't have the possibility to have easily the faults in the laboratory, so we create natural laboratories where we test different different strategies, let's say, to study the phenomena. And so if in future we want to discuss about the possibility to have some common sharing of expertise and if you set up some similar
I saw the possibility of constructing the natural laboratory in Japan, but we have many active faults. And but so which is the best place for
yes,
us?
okay,
So
yeah,
it's
yeah,
very
of course, yeah.
hard
Yeah.
question to us. So, so I want to ask you: so, how do you determine the three sites, basically?
Well, two were selected because were the two strongest earthquake recorded since instrumental seismology. Okay. So one was in the 1980 Irpinia earthquake area with the normal faults. So this is representative of the condition of central happening.
Okay. So is there still seismicity ongoing?
Yeah, the seismicity is ongoing there, and there is so the probability to have further large earthquake there. Yeah. The second was in our area, so Southern Alps, where we have thrust fault mainly, and there was the 1976 earthquake. So this is another example. And then there is a very interesting one, which is the Valtiberina Near Fault Observatory. That was the original one. So this was the first one, because there we have a low-angle normal fault, which is under creep. And so they selected this area and they improved the monitoring also with stations in deep hole, just to study the mechanism of creep. So our community selected these three sites, and then slowly we are trying to improve the knowledge in these conditions, and then to extrapolate the knowledge to the other place, because we are, unfortunately, have also a lot of faults.
Yeah, you have also.
So, but we selected three examples.
Creeping behavior is very interesting. So it's easy to target, but in Japan, unfortunately, we don't have any creep movement in the shallow cluster depths. So if you go to subduction zone, you have many, the slow slip, slow earthquake or something. But in the cluster level, we have almost no chance to see the creep movement. So. Okay, thank you very much.
Thank you. This time, okay. So thank you very much again to all of you. It has been really interesting, and I hope that we can continue maybe in the next future in Italy with another panel that you visit us and we continue to discuss. So thank you again.